Good morning, everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this session, we will talk about European multiple column curves. Before we go into multiple column curves, let us look at the evolution of column curves. We know that the Euler load is given as pi square EI divided by KL square, where E is the modulus of elasticity, I is the moment of inertia, K is the effective length factor, and L is the length of the column. KL is the effective length. So when we plot the load and the length, we get a parabola as shown here. But there is a problem with this curve. The problem is that there are infinite number of cross sections, and this curve will not be able to help or satisfy the needs that are required for the design codes. So you can see that there can be function of different cross section which gives different curves. So to avoid that, we need to move into what is known as stress versus slenderness ratio curves. So when we divide the Euler load by area A, we get sigma E equal to pi square E divided by KL by R the whole square. When we plot it, we have one single curve which is based on the slenderness ratio of the column. The slenderness ratio basically incorporates both the length as well as the cross-section properties. Length is given by L, the cross-section properties are given by the radius of gyration R, which is a function of I by A, because R equal to root of I by A. There is a problem with this curve also, because this curve does not consider the different squash loads that the column will experience. So based on the material strength, if it is a 250 MPa or a 350 MPa or a 450, 550, 690 or 700, so depending upon the squash load, this curve could change. So in order to remove that difficulty, we have to come up with what is known as a non-dimensionalized column strength curves, which is n dash lambda. Here n equal to sigma by sigma y. So we are non-dimensionalizing the stress, and the slenderness is also non-dimensionalized as lambda equal to root of sigma y by sigma e, which is equal to n, which is given by 1 by lambda square. Lambda equal to KL by R into 1 by pi root of sigma y by e. So when we plot n and lambda, we get one single curve regardless of the squash loads for the type of steel that we use. Here, the cutoff point is corresponding to 1.0. So when n equal to 1, sigma equal to sigma y, which means that the applied stress is equal to the yield stress. To the left side, you have stocky. To the right side, you have slender. The point at which it happens corresponds to 1.0. Now, let us look at the buckling research and code writing bodies, and followed by the column curves in national steel codes. Now, the focus is on buckling research and code writing bodies. In the US, we have three different code writing bodies: CRC, also known as Column Research Council; SSRC, known as Structural Stability Research Council; and AISC, which is the American Institute for Steel Construction. The CRC and SSRC are one and the same. The CRC is an old name, SSRC is a new name. It was changed in 1970s, I believe. Both are same. The CRC focused only on column research, whereas SSRC considers that stability is not only for columns, but it can also be for beams, plates, frames, shells, arches, so on and so forth. Then we have AISC, which is the American Institute of Steel Construction. These three are the code writing bodies in the US. In Europe, we have ECCS, which is the European Convention for Constructional Steel Work. In UK, we have the British Standards Institution, and in India, we have the Bureau of Indian Standards. The corresponding column curves in the national steel codes are: for CRC, we have CRC basic column curve. For SSRC, we have SSRC multiple column curves. For AISC, the column is simply based on the CRC column curve. For ECCS, we have ECCS multiple column curves incorporated into most European national codes. Now let us look at the multiple column curves. The multiple column curves as per EN 1993 1-1 is given by the Perry-Robertson formula. Recall that sigma y minus sigma p into sigma e minus sigma p equal to eta into sigma p sigma e, where eta equal to 0.003 into L by R. The 0.003 represents the Robertson constant, and we have sigma p by sigma y equal to 1 by p plus root of phi square minus lambda square, which we derived in the previous sessions. Phi equal to 1 plus eta plus lambda square by 2, lambda square equal to 1 by n equal to sigma e divided by sigma y. Eta, which is a non-dimensional imperfection parameter, is given as delta naught by c. C is represented as r square by y, which implies c equal to I by ay, which also means that c equal to z by a, where z represents the section modulus. The modified peri-multiple column curves can also be obtained by taking eta equal to beta into L by R. This expression is very suitable for curve fitting. So you can see that when we plot the sigma p by sigma y in the y-axis and lambda in the x-axis for various values of beta, we get a nice curve. This one you see is for 0.003, which is the value of beta for imperfection. And we have 0.001, which is a lower imperfection, which means that the curve is more convex. Then we have for 0.0035, which is slightly more than 0.003. And then we have 0.0055, which is yellow color. And then we have a much more aggressive imperfection where it is 0.008. The curve is slightly turning into concave. And what we have next is the Euler curve. You can see that with increase in the beta value, the curve turns from convex to concave, which means that it begins to lower its load carrying capacity, which means that higher the imperfection, lower is the load carrying capacity. So the load carrying capacity of the column decreases as imperfection increases. However, we should note that this curve does not take into account very short stub columns. The stub columns test results suggest that there should be a cutoff plateau for very stocky columns. Now, how do we take that? We use the same formula. We have sigma y minus sigma p into sigma e minus sigma p equal to eta into sigma p sigma e, which is the Perry's equation. We simply modify eta equal to beta into L by R minus S naught. From this equation, we know that L by R is dimensionless, eta is also dimensionless, and beta is simply a number which is again dimensionless. Therefore, S naught should also be dimensionless. We know that lambda equal to root of sigma y by sigma e, which implies lambda naught equal to kl by r naught into 1 by pi into root of sigma y by e. So we simplify this further. Lambda naught into pi equal to root of e by sigma y is equal to kl by r naught. So this becomes S naught is equal to lambda naught into pi into root of e by sigma y. So now, to arrive at the cutoff plateau lambda naught, the Euler curve was drawn with E replaced by E sub s, which cuts the line sigma equal to sigma y. It was arbitrarily taken as Es equal to E by 25. So when we plot it, we get this following curve. Here, when we look at the plot, we have the lambda value as 0.2, which is the cutoff point, below which there is extremely stocky columns, to the right of which you have practical columns followed by slender columns. So we have the curves A, B, C and D and the corresponding beta values as 0.0020, 0.0035, 0.0055 and 0.0080. And these are all values. When we plot, we have for A 0.0020, we have a curve that is shown here, and the red color one for B, which is 0.0035, the green color one, which is 0.0055, and D, which is 0.0080. This is for a value of sigma y equal to 275 MPa. We know that lambda equal to L by R into 1 by pi into root of sigma y by E. So when we substitute this value of L by R in the eta equation, we get eta equal to beta into bracket open pi into lambda into root of E by sigma y minus 0.2 pi into root of E by sigma y. This gives rise to the value eta equal to beta into pi into root of E by sigma y into lambda minus 0.2. Now this value of beta into pi into root of E by sigma y can be termed as alpha, which is the imperfection parameter. So alpha equal to beta into pi into root of E by sigma y. And in European Code 1993 1-1 clause 6.3.1.3 gives the value of pi into root of E by sigma y is equal to 93.9. This value can be obtained by substituting E equal to 2.1 into 10 power 5 Newton per millimeter square and sigma y equal to 235 Newton per millimeter square. When we substitute this value, we get 93.9. So, alpha now becomes alpha equal to beta into 93.9. So, now when we have to compare the values with the existing European codal provisions, we have alpha equal to beta into 93.9, and the imperfection factors for buckling curves as per table 6.1 is given as A is 0.21, B is 0.34, C equal to 0.49 and D equal to 0.76. When we substitute these values in the equation alpha equal to beta into 93.9, we get the corresponding values of beta, which is for A it is 0.0022, for B it is 0.0036, for C it is 0.0052 and for D it is 0.0081. So, when we compare this one with the buckling curves that are given in the European codes, we see that we get exactly the same as what we have derived in terms of the chi factor, which is the stress reduction factor, and then the phi factor again is exactly the same as we have derived in the European code. Now, this curve gives you the 5 different curves. It is not just 4 different curves, it is 5 different curves. We have one more additional curve, A0, which has the least amount of imperfection, A0, A, B, C and D. And these column curves are very similar to the column design curve that is used in IS 800 2007, except that the IS 800 2007 does not contain A0. So, section 7 gives you the design of compression members. Again, we have similar equations that we have already derived, can be seen in the codal provisions. The imperfection factor given in table 7 in IS 800 are also identical to the ones in the European code. And the one that you see on the left side is the IS 800 column curves. It is very similar to the European column curves, except that there is no A0. So, we start with A, B, C and D. Now, when we look at the multiple column curves as per EN 1993 1-1, we have this imperfection factors for buckling curves A0, A, B, C and D. Now, having understood the imperfection factors, we need to select the buckling curve for a cross section. The table 6.2, the European code gives you the cross section. It also gives you the limit. It also gives you the buckling about the axis, following which you have to define your buckling curve. There are 3 steps involved in this. The step 1 is basically to choose the H by B ratio. H by B ratio is the aspect ratio. H is the depth of the cross section and B is the width of the cross section. When H by B is greater than 1.2, then you follow the first 2 rows, and when H by B is less than 1.2, you follow the rows 3 and 4. Now, step 2 is to take into account the thickness of the flange. So, here there are 2 categories. One is thickness less than 40 mm and another is thickness between 40 mm and 100 mm. When the thickness is less than 40 mm, you are allowed to take a higher strength curve, whereas when the thickness is between 40 and 100, you are going to have a knockdown factor where you will have a lesser column strength curve. The one which is less than 40 mm, you are allowed to take higher strength curve. So, when the thickness is less than 40 mm, it leads to a ductile failure, whereas when the thickness is greater than 40 mm, it leads to a brittle failure. And then the third one is the buckling about the axis YY, which is the major axis, and ZZ, which is the minor axis. Having said that, let us look at the buckling curves here, A0, A, B, C and D. Now, what are these buckling classes A0, A, B, C and D? How do we classify them? On what basis? More importantly, is there a rational basis to it? So, the answer is yes, there is a rational basis to it. The research carried out in Europe by Beer and Schulz in 1970, Jacquet in 1970, Fintesco in 1970 led to the development of multiple column curves, which was later adopted by ECCS. The references can be seen here 1, 2 and 3, and the curves based on research carried out in Europe is given on the right side. You can see that there are 5 different curves A0, A, B, C and D. For each curve, they have given the cross-section shape, the manufacturing process, as well as the axis about in which it is buckling. And you can see that curve A and curve B, curve C, and curve D. The values of the imperfection factor as well as the buckling classes was thus determined based on the above conducted research on various columns. A similar multiple column curve was also developed by Behovde and Tall in North America in 1970s. This research was carried out at Lehigh University in Bethlehem, Pennsylvania. The research report corresponding to that is shown at the bottom, where Behovde and Tall uh, came up with this research report, maximum column strength and multiple column curve concept at Fritz Engineering Laboratory, Lehigh University. You can see the column curves at the top, and it is very interesting to understand how these column curves came into existence. Now let us look at more closely the column curves and the basis behind all this stuff. Let us look at curve A. The first cross section that comes here is the tubular cross section. We have a circular cross section as well as a square cross section. Can anyone guess why these circular and square cross sections are considered as curve A? It is simply because the moment of inertia in both the axes are almost the same. For square sections, the IXX and the IYY are the same, as well as for a tubular section, which is a circular section, we have the moment of inertia is the same in all the directions. Also, the J factor, since it's a closed cross sections, the torsional constant J is much higher compared to the open cross sections. The J here is given by 4a square divided by integral of ds over t, which we will cover in the beam section. But here to give you a glimpse of what we are trying to understand here is that two things that favor the tubular sections. One is that the cross section properties, which is basically the moment of inertia, is same in both the directions, xx as well as yy, as well as the J factor, which is much higher in a closed cross section compared to an open cross section, making sure this ends up in curve A. Now let's look at curve A and curve B. Here we have a rolled cross section W highlighted in red color box and whose aspect ratio is greater than 1.2. Now similar one is also there in curve B, where it is also a rolled W section, white flange, and H by B is greater than 1.2. The cross sections are the same except that the buckling about these cross sections are different. The one that is given in curve A is buckling about major axis, where the residual stresses will favor the major axis buckling, whereas the one given in curve B, where it is buckling about minor axis, in which case the residual stresses will not be helpful, and hence it has been put under curve B. Now let's look at the another cross section, which is basically white flange rolled W, H by B is greater than 1.2, which is in curve A, and we have the same cross section rolled W, but here H by B is less than 1.2. The aspect ratio is 1.2. So when the aspect ratio is less than 1.2, the buckling capacity is much lower, and hence it has been put in curve B. So both of them are same, both of them are rolled, both of them are white flange shapes, but except that one has an aspect ratio greater than 1.2, so it finds a place in curve A. The one with aspect ratio less than 1.2 finds a place in curve B. Next, let's talk about the curve B and curve C. Here we have rolled W, H by B less than 1.2. In curve C, we have rolled W, H by B less than 1.2. Both of them are same. Again, the curve B, it is buckling about major axis, whereas in curve C, it is buckling about minor axis. The one that is buckling about major axis will find a place in higher curve simply because the residual stresses favors the major axis buckling, and hence it is in curve B, even though H by B is less than 1.2, whereas the rolled white flange section H by B less than 1.2 in curve C is buckling about minor axis, where the residual stresses is not going to help you, rather it is going to hurt you, and hence it is finding a place in curve C. Now let's look at the two other things where it is welded H flame cut as well as welded H flame cut. FC refers to flame cut. So the one in curve A is about major axis buckling. The one in curve B is about minor axis buckling. So the same explanation holds good. The major axis buckling will have a higher strength due to favorable residual stresses. The one in minor axis buckling will have unfavorable residual stresses, and hence it is put in curve B. Now look at another comparison. We have welded H FC, which is in curve A. FC represents flame cut, and then the one in curve B has welded H UM. UM represents universal mill. Both of them are same except that the fabrication process is different. Flame cut will lead to lower residual stresses, and hence it finds a place in curve A. UM, which is universal mill, will have a higher residual stresses, and hence it finds a place in curve B. Next, we'll talk about welded HUM versus welded HUM. Both of them are the same manufacturing process, except that the one in curve B is buckling about major axis, whereas the one in curve C is buckling about minor axis. As discussed previously, the major axis buckling will be giving higher load carrying capacity due to favorable residual stress compared to the one with minor axis buckling. Now let's look at rolled W with welded cover plates that are present in curve A, and then rolled W with welded cover plates that are present in curve B. Both of them are same, except that in curve A it is bent about minor axis, whereas in curve B it is bent about major axis. It may find strange why something that is bent about minor axis finds a place in curve A compared to the one that is subjected to major axis. It is simply because the additional plate that is added on top of the W section will be much more effective when it is bent in minor axis, because it has a more width. So the B cube effect will be more, and hence it has higher moment of inertia compared to the one which is subjected to major axis. Here the cubic effect will be T. So T cube will be there, but T is very small compared to B, and hence it finds a place in curve B. Next, when we compare about welded box annealed versus welded box. So the one with annealed has superior residual stresses compared to the one without annealing, and hence the one with annealed one finds a place in curve A compared to the one with welded box without annealing finding a place in curve B. Now the last one that we were looking at here is that we have a cross section which is wide flange and H annealed and rolled W annealed. One is in curve A and one is in curve B. Similar argument, the one in curve A is subjected to major axis buckling. The residual stresses favor major axis buckling, and one in curve B is subjected to minor axis buckling. The residual stresses do not favor minor axis buckling, and hence it finds a place in curve B. Now let's look at the last two cross sections in curve C, which is a T section and a channel section. Both of them are singly symmetric. So the singly symmetric cross sections have much lower load carrying capacity compared to doubly symmetric cross sections, and hence they are placed in curve C. And then we have the curve D, which is basically heavy shapes. The shapes are not determined. It could be arbitrary as well. So all those things that do not fit into curve A, B, and C comes under curve D. With this one, we have completed the multiple column curve approach. I think we have given a good understanding of the development of the codal provisions, and we will come up with more discussions in the next class. Thank you very much.